Yeah, so I'm going to talk about some simulations using the AUS2200 setup, which is the 2600 by 2120 grid points at 2.2 kilometer resolution. And we've been looking at sea surface temperature sensitivity experiments with various different sort of inputs for the sea surface temperature. We've worked on 4 simulations so far. The first being a climatology, which is a 3rd of June average skin temperature for 1980 to 2019. And then our fixed is fixed on the initial time of the case. And then an evolving has the skin temperature updating every day. And then a smooth one is removing a warm eddy that seemed to be potentially impactful. And this case was a real heavy rain event, extensive heavy rain event that affected most of Eastern Australia from southern Queensland up through New South Wales and into Tasmania. And this just shows that there was, I wanted to show this animation on the 5th because during this case there was the development of a subtropical type cyclone at East Coast Low, which are East Coast Australia is known for. And if I go to the next slide, this is a zoomed-in image just showing the Sentinel-3 off the coast. So the storm actually remained off the coast. There's some discoloration of the water, which is due to the high winds. And then the ACCESS scatterometer also got this pass. So although it's mostly rain flagged, it's a strong tropical storm strength subtropical cyclone, at least. So quite a strong system. So the 2 cases I'm focusing on are the climatology and fixed. And the climatology is on the left, and this is just zooming in to a section of the domain off the coast of New South Wales primarily and off Tasmania. And the main thing to note here is that at the time there was this warm eddy. Warm waters generally, if you look at the same latitude, it's warmer all along the coast at the start of this case compared to the average for the same day across this period. And that stretches down to Tasmania as well, and then it's kind of back more to the normal as you get further to the south. The anomalies look like this, and this is the difference between the 2 cases. And you can see that it's actually a bit cooler than normal off to the southwest, but then much warmer as you go into these warm eddies off the east coast. And you see the Coral Sea and up in the tropics, it's all above normal. And actually this was really exceptional at the time. The Bureau, in their special climate statement, produced this graph, which is the average across the seas, the anomaly average. And for the Coral Sea and the Tasman Sea, you can see it's the final point, which is for May in the lead up to this event. It was warmer, the warmest it's ever been recorded up to that point, with the Tasman Sea being maybe something like 3/4 of a degree warmer than had ever been experienced on the average for that time for May. So quite exceptional conditions. So this is what our simulations look like. And I've included the evolving one, which acts as a comparison with the fixed. And when you look at these simulations with the different sea surface temperatures, they look pretty similar. You've got the broad structures, very similar. And if I stop it at a point, say like here, there are some things to note. Even though it may look generally similar, there are some significant differences. In both of the ones that use the observed SSTs, the low pressure is somewhat more intense, and it's also held further to the north up the coast. And then if I go forward in the simulation, and I stop it there, the climatology has one distinct low pressure system over Tasmania, while the fixed and evolving, which use the observed SSTs, both have multiple low pressure systems around Tasmania at this point. So there are some differences, even though the broader circulation appears similar on first sort of view. Oh, so that goes backwards. All right. How can I get forward? How do you go to the next slide? Okay, thanks. So this is the rainfall difference on 5 days across the simulation. And the main thing here is that the rainfall is quite a complicated pattern with pluses and minuses over the ocean. But if you look at the New South Wales coast in particular, it's very clear signature of increased rainfall pretty much along the length of the coast. So this is quite interesting, as that was the area that was so heavily affected by the rainfall. But Tasmania doesn't seem to have much difference at all, which is curious. Nonetheless, it looks like there's something interesting happening here, where the complicated patterns off the coast are translating to a more distinct signature when you get that forced uplift over the mountains. But I haven't looked at this in detail. I've been mainly focusing on the low pressure system. And this just focuses in on the lowest pressures. And so if I stop this simulation about there, when we look at the climatology and the fixed, you can see that the fixed now has a lower pressure. It's at about 987 millibars, and it's also held slightly to the north. And the climatology is slightly higher pressure, so it's a less intense cyclone being developed. And then as we progress, we see that multiple low pressure system developing off Tasmania in the fixed case. And this was actually seen in the Bureau analysis, where you have these multiple low pressure systems, and also these are at the same time with the low pressure held somewhat further to the north in the Bureau analysis. And this is if you can subtract the two simulations, so this is the fixed simulation minus the climatology, and in this way, underneath are the sea surface temperature differences between these two cases, with the dashed being negative. And if we play this, what you're seeing is the response in the sea level pressure from these changing sea surface temperatures at the lower boundary. And at the start, you see a general kind of lowering the pressure over the warmer SSTs. And then you see this sudden kind of distinct signature as the system, that particular subtropical cyclone, moves towards the storm, and then this big difference between the climatology and the fixed. And that then maintains, and this is why you get that difference in the structure of the low. You've got this kind of anomalous low pressure forcing the situation. And we can also look at the temperature difference, and thanks to Paolo Petrelli for helping me with the mopper to get this to work. This is 800 to 500 hectopascal, and this shows the deep tropospheric warming from those sea surface temperatures. And is that going to play? And this just shows that really you get like a signature from those warmer SSTs that is warming the deep troposphere. And then you see this kind of big warming, a large area that is 3 or 4 degrees above normal that develops as that low pressure system is rapidly developed. So this is the sea surface temperatures having an impact that is that gets concentrated. So by the end, you don't see differences in other areas. So I'll just quickly mention that we did also smooth out the eddy in order to see if the gradients around the eddy would have an effect. And that was just using a technique that brings in the climatology. And when you do that, actually, we basically just didn't really see much of an impact at all. So we're really kind of concluding that it was just the broader warmer sea surface temperatures that were responsible, and then that concentration over the coast. So really there's not too much to see here, just some small differences. And to summarize, yeah, we've seen this very interesting development of warming through the deep troposphere that gets concentrated off the coast and then leads to this rapid deepening of the low pressure.
Hi, very interesting. You've inadvertently stumbled into a hypothesis I've had for a while. What you're looking at is actually not a flow over a coherent eddy, but flow over a coherent boundary current. So if you go back to those SST patterns, you can see that there's a broad warm water signature flowing from more or less the New South Wales Queensland's border all the way down to Tasmania. That's consistent with a strengthened East Australian current. And I'm just here looking at the data out of our mooring array, suggesting that we had, just prior to this event, amongst the strongest southward transports through the mooring array, just prior to that event. So I think that smoothing out the eddy is not actually having a huge difference on the evolution of the system makes sense, given that it is the East Australian current that's setting up that broader warming along the shelf there. So just flagging that that's pretty cool.
Yeah, I'm really glad you mentioned about the strengthening current. Is that you observed the strengthening current bringing the warm water?
We did indeed. I'm looking at it right now on the ACCESS website.
Yeah, oh, fantastic. Yeah, I was really wondering about that. I looked at the satellite currents, and it looked like there was this kind of almost jet of water coming down prior to the event.
Yeah, cool. Ocean atmosphere coupled modelling. Get into it, people. So.
Got time for another question? Was there much difference between your fixed and your evolving simulations?
Yeah, I didn't really show too much of that. There isn't too much difference. They're pretty similar. So those three, the fixed and the evolving and the smooth, are quite helpful as like a very short ensemble of three cases, just to show the observed SST.
Yeah, cool. Thanks very much, Chris.
Hi, very interesting. You've inadvertently stumbled into a hypothesis I've had for a while. What you're looking at is actually not a flow over a coherent eddy, but flow over a coherent boundary current. So if you go back to those SST patterns, you can see that there's a broad warm water signature flowing from more or less the New South Wales Queensland's border all the way down to Tasmania. That's consistent with a strengthened East Australian current. And I'm just here looking at the data out of our mooring array, suggesting that we had, just prior to this event, amongst the strongest southward transports through the mooring array, just prior to that event. So I think that smoothing out the eddy is not actually having a huge difference on the evolution of the system makes sense, given that it is the East Australian current that's setting up that broader warming along the shelf there. So just flagging that that's pretty cool.
Yeah, I'm really glad you mentioned about the strengthening current. Is that you observed the strengthening current bringing the warm water?
We did indeed. I'm looking at it right now on the ACCESS website.
Yeah, oh, fantastic. Yeah, I was really wondering about that. I looked at the satellite currents, and it looked like there was this kind of almost jet of water coming down prior to the event.
Yeah, cool. Ocean atmosphere coupled modelling. Get into it, people. So.
Got time for another question? Was there much difference between your fixed and your evolving simulations?
Yeah, I didn't really show too much of that. There isn't too much difference. They're pretty similar. So those three, the fixed and the evolving and the smooth, are quite helpful as like a very short ensemble of three cases, just to show the observed SST.
Yeah, cool. Thanks very much, Chris.